Well, then let's begin. Let's go to slideshow, and here we go. Yeah, so since it is the very first meeting of this kind of group, I try to choose the topic that should be, let's say, kind of provocative. So it's about like quantum era that is already all around, but what are the limitations of like quantum algorithms and quantum AI algorithms for business? So because I mean, like, still, as I said, the final target is to have some application case in business. So we're gonna exactly speak today how it can be done then for business. Okay, let's move on. Come on. Yeah, cool. So how I see business. I mean, I was working in industry, I think like in total for about 7 years before I moved fully to academia. And what I remember is that business is always selling something. So I mean, like the main idea is that if you are a business, you want to have clients and you want to have some product for clients. And basically this is all about obviously like selling things. That's why today I chose the traveling salesman problem as the basic problem that we're going to be looking at, and then finding out what are, let's say, the current solutions around this problem. And as you understand, this is very business-like problem. And just for those of you who knew about this problem but totally forgot about it, just a quick reminder, yeah, that I'm, let's say, a travel salesman long time ago. I want to visit all the cities. I think originally it was somewhere in Europe. And then basically what I know is that I have a list of cities and I have distances between each pair of cities. And basically, I want to make my route as short as possible, yeah? But I want to visit each city. And I want to visit each city exactly once. And let's say additional condition is that I want to return to origin city. So this makes sense because I basically really want to sell everything around and come back home, most likely in the evening, yeah? So this is it. This is the list of cities. And on the right, you have exactly the optimal path. Yeah, so this is how it should be ideally. But in reality, this occurs to be NP hard problem. Yeah, so this is the problem that is hard to solve, but it's very easy to check. Yeah, so this is the problem that if you give me a solution, I can easily verify that it satisfies the conditions of the task. But to find the solution itself, this is not that straightforward. And let's say, let's first go like how to solve it directly. Yeah, you can have like the direct solution. You can just, I mean, imagine, yeah, the most stupid algorithm. You just start comparing all the possible pairs, yeah, and trying to figure out that this is one set of roots. This is another set of roots. The problem is that the set of roots is not polynomial, yeah, but it is exponential of the number of cities. So that's why finally, this is like super hard problem. And if not to solve it exactly, I can try to allow some, let's say, not that strict limitations, yeah? I can, for example, get something that is called genetic algorithm, and this is now how we're gonna be moving today. So I would like then to show this kind of pathway from the most stupid solution, a little bit smarter solution, maybe with some inspiration from biology or physics, and then finally quantum solution. Yeah, so basically because first we're going to have some inspiration from sciences, from natural sciences, and then we're going to have a fully like natural science solution. And if you ever use genetic algorithms, you definitely understand how it's going to be solved in this case. But if you didn't, no problem. I'm going to just quickly tell you. And this is the picture that exactly demonstrates the power of genetic algorithms. So majority of you are data scientists in past or in present. You know that before all this stuff about backpropagation came into power, I would say genetic algorithms maybe were one of the top, let's say, solutions like before this era of just general machine learning. Yes, so still genetic algorithms, I would say, are still used quite a lot in hyperparameter tuning. So if you go to some tool like Optuna, I would say like one of the most optimal is to choose is like genetic algorithm. So in our case, we use genetic algorithm not to fine-tune parameters, but to solve exactly the problem, yeah? So how it works, you're gonna take, let's say, I'm gonna suggest you one set of solutions, yeah? I'm gonna say that this is solution, this is solution, this is solution, yeah? And then you're gonna try to kind of mate them together, yeah? So obviously, if I give you random solutions, they are not optimal, yeah? But if then I'm gonna start mix and match of these solutions, yeah, and seeing that they satisfy the condition, then basically this is the idea of Darwin, yeah. So then basically those that are bad solutions, they gonna just extinct, yeah, and those that are nice solutions then gonna survive. And then by mix and matching of bad solutions, finally in the end, I'm hopefully getting a good one, yeah. And as I say, this is probabilistic. So it means that I do not have guarantee that in the end, I have like the best solution. But as it is said, I mean, and there are like proofs of theorems around all these theories that I'm going to have good enough solution. So this is how it is formulated, good enough solution. Okay, so let's say that we have already good enough solution, but I want to have something better. I now get inspiration not from biology, I get inspiration from physics. I go to physics and say like, hey, come on, I have heard that there is such a stuff that is called simulated annealing. And again, as we understood from your fun facts, a lot of you have background in physics. So you definitely, and as we know that you are plus data scientists in past or in present, meaning that you also know that before this optimization, yeah, via backprop, like the way how you were trying to find out the optimum was, for example, simulated annealing, yeah? So you have some high temperature in the beginning, yeah? So you are saying that your system is very chaotic. And then basically you're, for example, in this case, yeah? I'm taking some bad route, yeah? And in the end, I'm trying to see, okay, other like neighboring routes, yeah? That differ not too much, yeah? And if, let's say, the neighboring route is better, I'm choosing it, yeah, for example, or I'm leaving the one that I currently have. And this is based on temperature. So, I mean, in the beginning, I can randomly choose whatever, let's say, non-optimal solution. But as long as the temperature goes down, I'm gonna be exactly, hopefully, choosing better and better solutions. So, since there was this problem that you do not have this strict guarantee of good solution, obviously people were trying to choose to find out something better, and this is how, let's say, backpropagation idea came, yeah? Because there you definitely have these ideas of how to avoid, for example, local optima, yeah? So there you, so I mean, because these simulated annealing with the good algorithm, yeah, it's gonna be long, it's gonna be hard, but you almost have guaranteed to find the global optima, yeah? But again, it's gonna be long, so, and this is kind of the main problem. So unfortunately, we would need like more time resources. But still, I can make simulated annealing and find any solution for our travel salesman. But what else I can do? I can go for quantum. And in order to demonstrate you now a little bit of quantum, I understand that all of you, yeah, maybe it's gonna be not that interesting, but now let me show you something. So I don't know if you ever played tic-tac-toe, very simple game, yeah? But I can show you a little bit, let's say, interesting version of tic-tac-toe, which is called quantum tic-tac-toe. This one is implementation from guys from Netherlands. Very interesting stuff. So, I mean, what's more interesting, what I was surprised with is that it is now used in schools in Netherlands. So, I mean, like in high school, children in like some parts of Amsterdam, they are using this during their courses. So basically, what we can do, we can make a simple move, yeah? Like here, cross, yeah? I can make a simple move here, yeah, in center. But what I can do, I can now show you. Move like this. And this is demonstration of quantum superposition. So basically what I did, I say that I'm not gonna put cross in one cell, I'm gonna put it in two cells at the same time. But only in the end, I'm gonna, this game gonna tell me where the cross is. And this is kind of this principle of uncertainty, yeah? So basically, we're saying that cross could be here and here, yeah? But I don't know yet. Okay, let the other player do the same. I'm gonna also have some uncertainty. Then I'm gonna have some uncertainty here. Okay, and now I do not have like the way to do. I'm gonna make it here. And this is what happens, yeah? So you see, after happens such a called measurement. So those of you who are from physics, it is obvious. So basically, you had like a coin flip, yeah? So coin, it has like two sides, and only in the end, I'm gonna tell stop, and it's gonna be told if it is like which part of coin it is. And here it happened the same, yeah? And then now I continue playing, yeah? Basically, but since now whose turn it is? It is cross, yeah? So obviously I'm gonna most likely put cross here, but okay, let's say that I'm stupid. I'm gonna make this move and now make measurements. But you see, there was no difference. Either way, here or here, I'm gonna win, yeah? If I play 4 zeros. That's it. So this is quite an easy way of how to introduce superposition. And yeah, I'm gonna then send you the link to the presentation. You can play it. I would say that I have seen how kids really enjoy it, so you can play with kids. So something new, because you know, like old tic-tac-toe, everybody already knows how to play it. But here, something not that easy. Okay, good. So yeah, I think, yes, this is exactly just to formalize it, yeah? How we gonna be using it? So in our case, we're gonna say that, okay, we have like not a coin, yeah, but we have like bits. And in case of classical bits, it is easy that it is either 0 or 1. But now I'm gonna be using this kind of ball. And this ball is gonna be rolling. And I tell you in advance that when it stops rolling, it could be either here, it could be landing, yeah, either on this pole or on that pole on the top. And if it is on the top, it's going to be 0. Yeah, it's going to be 0. Otherwise, it's going to be bit 1. So it means that now what I'm going to be doing, yeah, during my quantum algorithms, I'm going to be trying to use this principle of uncertainty of probability of event. So just let's see how it is done. So basically, why I'm giving this idea? Because this is the paper, I think, from last year. So very fresh one. It's called Solving the Traveling Salesman Problem Using a Single Qubit. So these bits that are not exact, not 0, 1, or just I mean, which are both 0 and 1, they are called qubits, quantum bits. And I would say that I really enjoyed this paper. You can then visit like the link in description to the slides and just read how they were able to then converge this problem. So yeah, so original traveling salesman problem, they finally were able to convert to the problem of finding the path of shortest travel time from a particle falling under uniform gravity. And you know, like here, the point is that the optimal path is like not the shortest one, but the one that brings you like the smallest time of travel. So this is kind of very interesting thing. So I really recommend you to go through this later. But this is the point of solving it with quantum. So basically, each city was represented as quantum bit. And then this kind of path, it was, you see, depending, yeah? So the path length, it was like a condition. And basically there was the idea of kind of, let's say, falling from one city to the other one. And this is, I would say it's absolutely amazing. So really this stuff that how people can approach it. So yeah, me, myself, I would never think about it. What me myself can think about it is, for example, this one. So this is not quantum algorithm anymore. Yeah, this is already AI, because then you might tell me that, come on, everything is now solved with AI. Maybe let's do it with AI. There are 3 brave guys who tried to solve it with GPT. They said, come on, let's take GPT, you see, it was like even, I think, last year, GPT 3.5 Turbo, and they tried to solve a travel salesman problem with the idea of giving like conditions to GPT and then trying to get optimal path. I mean, you can read this paper. Of course, it was not accepted anywhere. Yeah, so I mean, like it is still on archive waiting for its best moment. I think maybe because the GPT 3.5. If they do it now with GPT 5, it's gonna definitely go through. But it's half a joke. So because I mean, like this one, I mean, it worked for basic cases, yeah? For more complicated, obviously not. But there is a nice paper in not Nature, but you know, there is Nature, nature.com, and there is Springer Nature. So this is from Springer Nature. And this is like a big overview paper, very recent one, so June of this year. It is about solving travel salesman problem with AI. And basically it goes through all the possible articles that were trying to solve it. And I mean, I went through the paper, I can tell you in advance that for simple cases and even sometimes from middle cases, it might work, yeah? When it comes already to like super complicated, it still unfortunately stays like NP-hard problem, yeah? So we cannot still say that, we solved it, yeah? So, but come on, jokes aside, AI still can be, let's say, if not like the one I presented at the previous slide, but at least physics inspired. And I think maybe even some of you already used, you know, this, now it's called, I think, PIN, like physics informed neural networks. So if you didn't use it, today we're going to discuss it a little bit, but this is quite an interesting idea. At least I find it quite an interesting, though I have heard from a couple of physicists that from physics perspective, this is all bullshit. But I mean, like, again, because like this is the example, yeah? So I mean, I definitely know that you know how standard neural network looks like. But what comes in, let's say, inspiration from physics or information from physics is that you have some ideas on constraints of how your system behaves according to the laws of physics. And what you do, you then add these constraints to the regularization. So this is basically when you're going to look at physics-informed networks, this is what you're going to find. You're going to find that these are additional regularization terms, and sometimes it really works. So for example, so I mean, there are really good, again, so this is the paper from last year, and it is, I think, from Nature Scientific Reports. Yeah, not the worst journal. Very nice one. So here there is like the use case of, as I said, yeah, in some cases it really works. And for example, this is the case of pendulum, and it's like modeling of the torque scenario in swinging up pendulum. And what is interesting that when the system itself comes from physics, yeah? So I mean, like there, obviously, the system should behave according to some physics laws, yeah? And before, this is very interesting, yeah? Before this idea of physics-informed neural networks came, this task, it was never solved with this information included into regularization. It was always all the information that was coming, it was coming in the beginning, it was coming in the conditions, so it was like kind of conditional solution, but it was never added like this to the regularization. And I would say that's why this is the first like really powerful solution in terms of having the laws of physics taken into account. Okay, so that's why you see. So basically, this could be solved with some physics things, but why not to play once again and to just show you a little bit more of quantumness, because let me start the game here. You remember, yeah, how I can play? I can play like this, I can play like this, I can play like this, and now what I can do, I can play, come on, no, I cannot play. Guys, I'm sorry. As I said, this is like our first meeting. Let's do it once again. Boom, boom, boom. Come on. No, it should work. Start game. 1, 2, 3. Here it works. Great. So basically, this is the illustration of entanglement. Entanglements, again, quick reminder. So superposition, now it is clear, yeah, that we have superposition in terms of like being like cross, yeah, or O in two cells at the same time, and then finding out only in the end where it is exactly. And entanglement is even more interesting. So you see, first I made a move. And then the other player said, let me entangle with you. Yeah. So basically, entanglement, this is how physics implements if else kind of condition. Yeah. So basically, it says that if this gonna be measured, like for example 0, this gonna be 1. Yeah. If this gonna be measured like 1, this gonna be 0, and etc. etc. So in entanglement, this is like this, as I said, if else condition. You should have somebody controlling, and then somebody like obeying how you gonna then end up, yeah? So, and this is what happens. So basically, entangling means that, if I'm not mistaken, we need to read the rules of games. I think that if here it's measured like X, then here is measured O, and I think like vice versa, it would not work. I think like if here it's measured O, then this X should be measured. So basically, you see, yeah, so how it now works. So there are here two O's, and it's entangled, and here this is X. This is X staying here. So let me just quickly then have this game. So I'm going to have like this, and I think now I can, let me just play like this. Oh, you see, I was lucky. I was very lucky. So entangling worked for me, but entangling can work not for you, yeah, obviously. So the other day it's not gonna work. But entangling, let me just maybe let us skip it for now. Entangling is one of very cool properties that can be then used along with superposition. In order to do what? In order to enhance, for example, AI. I'm not gonna take too much from the bread that Frederick is eating today, because the topic of his talk is like quantum AI from lab to business. But if you don't mind, Frederick, maybe I'm just gonna give a little bit, yes, so just a little bit of stuff. So like, what is going around, yeah? So what can we do with this type of, let's say, AI? We can, for example, take the stuff that is called quantum support vector machines. So support vector machines were very nice and brave in the beginning of the era of AI. Then other methods came, and support vector machines, already nobody remembers how to use them. But then quantum comes, and quantum says like, come on, entanglement, this is the super cool stuff. So in fact, now, since we have in quantum neural networks, since you have also like quantum gradients, and you can train neural networks where you have like this possibility of connecting. So now imagine, yeah, your neurons, they could be connected with entanglement. So all the same stuff as it was. So like here, like here, yeah. So like original neural network, but then you can take your neurons and connect them with help of entanglement, for example. And this really gives you very powerful condition, since you have seen, yeah, this sphere, the block sphere, at which I was like calling a ball that is rolling. It has, it operates in higher dimensional space, yeah? So basically, we are talking about the Hilbert space. And there, of course, you can imagine that it really meets this idea of kernelization trick, where you, without going into higher dimensionalities, you can measure, yeah, so with kernel, what is the idea of kernel? That you measure the distance between objects in higher dimension without, in fact, going into this higher dimension. And this is kind of the stuff that occurred to work really well if you go like not into classical space, but into the Hilbert space. And there you can model with this, since you now have additional, think of if else, this kind of connection. It occurs that you can model very complicated dependencies. The only, quick spoiler. So, I mean, do not then leave and stay for the talk of Frederick. So, I mean, but a little spoiler is that, for example, this particular technique, it occurred to be, as of now, let's say, most efficient on very artificial data. So, I mean, the data that was specifically created in order to behave according to these if-else conditions. But come on, this is just, you know, I'm from academia. I know nothing about how it works in business. So just listen to Frederick. But what I can tell you for sure, how people already trying to use it, and I would say this was quite a boom thing last year. It was this compactive AI. So this was the model that was using not exactly quantum. So I mean, it was not run on a real quantum computer on production, yeah, but it was trained on quantum computer. And basically guys were able, with help of these entanglements, they were able to make a super nice distillation of LLM and then to use it. And I mean, I think it was finally like reducing 70% the number of parameters, which resulted in severe acceleration, but with minimum loss of accuracy. So this was super cool thing. And I mean, if you wish, you can listen to podcasts. So this YouTube link, I leave it here. So this is the link to both the article on Archive and podcast on YouTube, where exactly the guy who created, I think it's first or last author, they're telling about how it is done. And I mean, just, I mean, for you, if you're gonna be then interested, because I know that a lot of you work with LLMs. So I would say that in general, this is now the topic, let's say drift that is called quantum knowledge distillation. So quantum QND, yeah, quantum knowledge distillation, QKD. So basically you can search for this and you find like a couple more works that are using this idea of quantum for distillation. I find it absolutely amazing. And this slide, I'm going to leave for those who are not yet sure about how to use quantum algorithms and AI in the business cases. But some of them we already discussed today, yeah? So we already discussed this route optimization. We discussed, I think, what we else discussed? We discussed nothing. So basically, that's why I leave this slide here. Yeah, so that now you have understanding of what it is used for. So for example, today, our talk from IBM, that's gonna be, so I mean, if you can, try to stay for the talk. It's gonna be super interesting. It's gonna be Almudena Carrera from IBM. So she is like super top researcher there, and she has a cool background in using quantum for financial analysis and also for molecular simulation. So this should be super interesting. So there's like, for example, here, yeah, this molecular simulation. And I mean, for example, from our side, from our research group, there was like the attempts to create some quantum autoencoders that are doing the detection of different anomalies. And in some cases, I would say it could be beneficial, but again, it's always the problem of scalability, and we're going to discuss it later. Yeah, so because the main question going to be like, why not everybody uses it? But now, before we go into why nobody uses it, if you wish, yeah, you can participate in a little quiz, because you see we have suites, and I think I have seen that nobody yet taken suites. So it means that suites going to be only for those who pass test. So just, yeah, we're in Switzerland, it's democracy. Want to participate, you do not participate, but if you wish, you participate. Okay, cool. So tell me if you need still time, somebody. Yeah, if you, okay, Rudy, I think you're done. Okay, good. Then let's go. So you join the quiz and we start. So first, myth or truth that HSBC is investigating quantum AI to enhance fraud detection and risk management. And also Goldman Sachs has been using hybrid quantum classical platforms to explore applications related to pricing financial instruments. So let's see if it's true or not, because basically from what I told you, this might be both, yeah? So, oh, come on, seriously? So you all think it's, okay, nice. Let's go on. So, myth or truth? Moody's is using quantum AI to predict the severity of tropical cyclones. This is already a little bit more complicated, yeah, because I cannot guarantee you that cyclones, they behave according to some quantum patterns, yeah. So as we were discussing, yeah, if it is strictly related to quantum, it's easy. If not, then not. Okay, 5, 4, 3, 2, 1. Let us see. Come on, no, guys, you didn't get the pattern. You see, it's more complicated. It's quantum. Okay, I give you the last chance. So, myth or truth? Volvo Research Institute uses data compression for further large image analysis, and it's about 2 million pixels. So, really large images on quantum computers. So, try to think. We didn't yet discuss it, yeah, but think if you can encode such a huge image into this quantum model. What's going to be the case? 4, 3, 2, 1. Okay, so here you are not sure, yeah? Okay, those who said myth, it's true. But come on, be attentive. It says Volvo Research, but it was Honda. So, I mean, guys, you need to be attentive. No, this is not how it works. Okay, so then, since you now know what is truth and what is myth, I can tell you what is the reality. The reality is that there are quite a lot of struggles. For example, this problem of why not everybody uses quantum algorithms around. So first of all, directly, it could be meanwhile applied to mostly like quantum natural data and processes. So for example, if you take like, I don't know, nuclear magnetic resonance, yeah, there you have already attempts of using it. So for example, you can speak to Clement, so he was using it there. Then for example, what other issues? That quantum machines, they are quite noisy. Yeah, so still, even though IBM already made quite a good progress with this, they are still noisy. Also, limited number of qubits. So I can tell you that, I mean, today Almudena gonna tell you more about, because like she works so like very closely to IBM machines, but let's say people who I know, they have like the order of hundreds of qubits for their researches, yeah? So meanwhile, not yet talking about thousands or even more. So this is still limited. Then early stage of algorithms, I would say that not really many people talk about it. But let's say after Shor's algorithm and Grover's algorithm, in quantum era, there was nothing in terms of boom saying that, oh, come on, this is the algorithm that now gonna change the future if we have, let's say, 6,000 qubits, yeah? Which is, for example, promised like about some classical algorithms. And for sure, price. I mean, for example, as institute, we get a little bit cheaper access, but I mean, still it costs, I mean, for example, one experiment. So if you're training your neural network, for example, or just some quantum algorithm, it could easily cost you like 5K Swiss francs. I mean, just single shot. So that's why I would say that, yeah, it requires quite a budgeting. But what I personally think about all these cases, okay, directly applied to quantum natural data, cool. I'm very happy about companies like Roche, Bruker, etc. So it means that they have advantage already now. Others just need to think a little bit how this could be applied. So it means that you need to find out if, let's say, your process somehow resembles something from physics. For example, you have some wave-like structure, or you have like some kind of this entangling idea of dependency between your data. Yeah, then let's say there are limitations in terms of like noise. Okay, so you can use simulator. So it means that you are not obliged to use the quantum computer. And for example, you can start with kernels, the one that I have shown you already today, because like kernels, especially if we're going to be talking about the kernels that you apply to image analysis, yeah, they're quite small. You can make small kernel, yeah, which is going to be going through your image, which is going to be like going with some window. And this one, having not too many qubits, require not too many qubits, you can run on simulator, for example. Then, limited number of qubits. Imagine that you have two quantum machines, yeah, 127 qubits, 127 qubits. Why not to connect them, yeah? So, okay, you're saying that I can build machines that are, let's say, not that prone to noise, that are like with maximum 127 qubits. Connect them and get more qubits. Why not? And I mean, of course, last two, they are very subjective. Early stage of quantum algorithms, come on, now the best people of this world are working on this. Yeah, you can join. As I said, yeah, those who are at this meeting today, both online and offline, are best people. And also price, yeah, price is high, but wait a little bit. I mean, like 5 years ago, the price was even like not like possible for universities to run real experiments, but today it's already much better. So let's get ready for the last call. So, no. Okay, you're not ready, yeah? Sorry. So you see, get ready for the quiz. Okay, couple more questions. Question number 1. Where is the closest quantum computer with more than 32 qubits? I mean, closest to this place, where we are sitting now. I have options: Basel, ETH, Toronto, or San Francisco. Let's see if you can guess where it is. 3, 2, 1. Go. Okay, I see that some people believe too much in ETH. Okay, the truth is that it is Basel, and today we have Frederick exactly coming from there. So he is going to tell you a little bit more about this supercomputer. Okay, and then the other question, as I told you, yeah, for example, why not to connect like 127 qubit computers? And in this case, it was that somebody first was able to get 142 qubits working, just connecting two quantum machines physically. Yeah, sorry, not physically, classically. So it means that they were connected, and this was success. Whether it was Google, Microsoft, IBM, or Meta, I excluded ETH, sorry. Okay, there are fans of like only Google and IBM. Nobody loves Microsoft and Meta. Okay, IBM fans, you are right. I can tell you more. Today, we're gonna exactly have a speaker who did it. So Almudena was the person who did it last year, and today she's gonna tell us about, I hope she's gonna tell us about how it was. If she doesn't, then we ask her additionally. Okay, nice. Oh, Rudy, congrats, you win. Sorry, I didn't tell you that then we're gonna have the leaderboard. So Rudy has today birthday. So this is congrats with your birthday, and all these sweets are for you. Okay, good. So then I'm already coming closer to my talk, and I'm just gonna give you my, let's say, idea of how I think now quantum should be treated, yeah? That if your business is super big, and you do know how to use quantum, then most likely you already have quantum team inside your company, or I mean, you're on its way, because I mean, this is the same about like Microsoft, Google, etc., etc. So I mean, they all have teams, and I can tell you even UBS had, I think, team till recent time. They were experimenting something, but now they transformed it, and it's going to be like already part of some department, but there was like a separate team. If you don't know, relax. So, I mean, your company is already big enough, so just chill. So seriously, or talk to me. Yeah, maybe we'll find out something, how to do it. Yeah. So if your business is a little bit smaller, then, I mean, if you know, then you directly can go to some in-Swiss project, or if not, then maybe you can use some third-party consultants that usually have like cheaper access to quantum and can help you with how to use it. Yeah. So, and I mean, the very last idea that I have is that you're going to have a lot of skepticals about quantum around. You're going to hear people saying like, quantum wouldn't work. But do you know this guy? CEO of NVIDIA, 14th January this year. Yeah, he says that quantum computers would not like exist as that we need them for 20 years, for next 20 years. Then June this year comes. Five months later, he says like, come on, quantum is already almost at inflection point. So you see, like, person in 5 months radically changed his opinion. So he was like straight right, now he's straight left. So that's why, I mean, it's changing so much that's why I would say that it would be really nice if we continue having these group meetings, like it's supposed to be like once in a quarter, yeah, in order then to keep updated about what has changed in terms of just quantum-inspired algorithms, what changed in quantum algorithms themselves, yeah, and in terms of both classical and AI things. So I would say that's it. So basically, somebody has already, no, that's it. So I mean, like this was question and answers, and somebody has already written questions and answers, Google Toronto. Yeah, so this is just, for those who are introverts and do not like asking questions, this is this Q&A. So I mean, like you can write them. But otherwise, that was it. I would say that maybe I was even a little bit shorter. So thanks for having me as your initial speaker. Do you have questions? Online questions, offline questions? I would say offline questions, maybe we can discuss during apero, which we have today, yeah, so celebrating Rudy's birthday. Okay, good. So if no questions, then I'm gonna I think, stop at this point. And yeah, thanks for guys online who were also with us. So I'm gonna stop recording of this session. Okay.